Hi, everybody. I'm Pamela Hughes, Director of Friends Programs here at the Institute, and it's my pleasure to welcome you and introduce the first speaker of this year's Lunch with a Member series, 2019-20 Friends of the Institute member in the School of Natural Sciences, Dr. Lena Murchikova. Last year, Lena was the Bezos member in the School of Natural Sciences, and you may have heard her talk in the spring on the discovery and exploration of the Milky Way's black hole with fellow panelists Scott Tremaine, Tim DeZoo, and Dimitrios Saltis. Before coming to the Institute, Dr. Murchikova earned her PhD in astrophysics at Caltech, where she was the Dr. and Mrs. Gross Fellow from 2014 to 18, and the National Radio Astronomy Observatory Fellow 2015-17, among other awards and honors. While at Caltech, Lena was a mentor for the Women Mentoring Women program, a research and teaching assistant, a moderator for weekly astrophysics discussions, and referee expert reviewer for MNRAS, one of the world's leading astronomy journals. Recently, she served as NASA Finest Referee, Finest standing for Future Investigators in NASA Earth and Space Science and Technology. In 2016-17, she was an affiliate of NASA Jet Propulsion Laboratory. Lena earned her preliminary degrees in theoretical physics at Moscow State University, where her first thesis was on radioactive effects in the Standard Model extension, and her second thesis on neutrino propagation in dense matter and electromagnetic fields. At Moscow State University, Lena was head instructor for quantum field theory graduate course, co-advisor and private tutor for mathematics Olympiad contestants, as well as junior research fellow and research teaching assistant. Widely published, Dr. Murchikova has many seminar, conference, and public talks at the IAS, and at the IAS, she's currently an informal seminar organizer. Amid all of her educational work, and here comes the fun part, Lena's expertise in astrophysics earned her a role as consultant in the 2014 blockbuster movie Interstellar, starring Matthew McConaughey, Anne Hathaway, and Jessica Chastain. IMDb explains the plot as a team of explorers travel through a wormhole in space in an attempt to ensure humanity's survival. Lena's job there actually makes her the Jessica Chastain character. On behalf of the Friends, I'd like to thank Dr. Murchikova for taking the time to speak with us today. Please join me in welcoming her as she talks about feeding a black hole. There'll be questions and discussion afterward.
Thank you so much. It's such a pleasure to be here, and it's a great honor to be invited. I'll try not to disappoint with all this. I didn't know I'm such a good person before I heard this introduction. And before I begin with the talk, I would like to ask you to interrupt me with the question while I go, because it would be much easier for me to judge which topic to concentrate more, which topic it's so obvious that no one is interested in. First of all, before we begin with the explanation of feeding the black hole and black hole physics, let me fly you to the black hole at the center of our galaxy. This black hole is located 25,000 light years away from Earth. In this picture you see, here is our sun, and here is the galactic center. And it's a schematic picture of the galaxy, which is supposed to look approximately like our own. The direction from Earth, where we're mostly able to see the galactic center, is from the southern hemisphere. It's just above there in Australia, while for us it rises sometimes just a little bit above the horizon. This is the brightest part of the Milky Way, so Australians have a much nice sky. In this region, I'm zooming in, and we get the constellation of Sagittarius and Scorpio. And our black hole is located in the constellation of Sagittarius, from where it takes its name, Sagittarius A star. It's covered with a very thick dust clouds, with a lot of gas and dust. And because of that, it's mostly seen in infrared light or in X-ray radiation. We cannot see anything from invisible light. If we zoom in into this little square right here, we'll see the structure, which is called mini-spiral. And I'll explain a little bit more about it in a second. But what I want you to pay attention to is this little dot right here, just above it. And here it is, our own galactic center black hole. This is just a little illustration how it could look like if an interstellar black hole was a Sagittarius A star. How do we know that our galaxies, this object in the center of our galaxy, is the black hole? We actually know it from observations, because people track the orbits of the stars around the black hole for 25 years. And this is what they see. This is not a simulation. This is observations. And you can see the years ticking up. There are much more stars in this region, but this illustration shows you only those which are very well tracked and the closest ones. And this is even more interesting observation, because if you look at this star, which was orbiting this one, which was going up, the yellow one, this one. Now you can see how it passed by the black hole in much higher resolution last year. So here it goes. And this is, again, this is not a simulation. This is a direct observation. You see 2 points moving with respect to each other. Why we conclude that this is a black hole is because this particular star passes so close to this object, and the object is so heavy that it can be nothing but a black hole. It cannot be a combination of nuclear matter, a combination of star cluster. It cannot be anything. It is a black hole. We know the mass of this black hole with the unprecedented accuracy. We know that it is 4 million solar masses, 4 million solar masses, more precisely 4.152. And this is because of this unprecedented pass by the closest star last year. I'll show you this little simulation which put in 3 dimensions motions of the stars around the galactic center, made by the leading group in the field located in UCLA in Los Angeles. You see the stars. The tracks of the stars is how much they pass during the year. And we're zooming out from the black hole. And we see that there is not much organized motions in the stars which are closest to the black hole. But further away, you start seeing the disk-ish structure going right here. All right. If in our own galaxy we are so close that we can track the stars moving around, what would we do for other galaxies? Because in other galaxies, there is only one of them on which the black hole is so big we can actually image it with the Event Horizon Telescope. For the rest, we shall rely on somewhat indirect methods. And the methods would be like this. So here is just one of the galaxy, which is M51. And let's consider the motion of gas or stars around the center of this galaxy. So we have these little stars here at two different radii. The velocity of those stars is due to the mass within the circle, more precisely within the sphere. So we know how much light coming from the galaxy. So we know how much stars are rotating. We see the motions of the spectral lines of those stars. Are they moving toward us, away from us? What kind of motion is this? So we see the profile of the stars moving in the galaxy, like linearly. And imagine if there is no black hole in the center of this galaxy. Then when you go closer and shrinking these circles, at some point there'll be almost nothing in them. So there will be no great attraction for those stars or clouds. And you'll see that the velocity will not going to extreme, not going to grow like crazy. But if there is a black hole, you'll go to a small radius, and the velocity keep growing because there is an object which is extremely heavy in the middle. And this is actually what we see and what we observe. Here is one of the galaxies. Along there is where we're taking the spectra. This line indicates where these molecular lines will be if we were just measuring them in our laboratory, moving with the same velocity as they are. Shift in the frequency of these lines tells you the velocity with which they are moving toward you or away from you. You can think about it from this point of view. There is a wave heading your direction, right? If the object moves toward you, it's kind of catching up with the wave. As a result, in frequency you receive, the wave gets shorter because the object is catching up with the wave while it's emitting it. While when it goes the other way, it runs away from the wave, and the wavelengths get longer. Therefore, if you see a shift which is toward red side of the spectrum, where the wavelengths are longer, this means the object moving away from you. If it shifts toward the blue side of the spectrum, the object moves toward you. So what you see here is a part of the galaxy is on the bluer side, meaning it moves away from you. It's like whole part of the galaxy from the center. This part rotates away from us, which is perfectly normal because this is just doing that, right? But in the middle, the velocity is going really high, really crazy, and you see these huge spikes in blue and in red. This is an indication of black hole being at the center of the galaxy. In fact, most galaxies have a black hole. And when I say most, I actually mean, I think there is one galaxy which is, we believe there is no black hole in it. So most of them have a black hole.
Excuse me, but
yes.
That's not true for dwarf galaxies, is it?
True. But those might be different way of forming them because they're too small. That's correct. Thank you very much for correcting me. If we look closer to the black hole at the center, it's a very big mass. It's creates a lot of gravitational potential. It's kind of make a funnel. And as we all know, if we have a funnel, say on a rubber surface, and we spray the beads around, they tend to concentrate toward the center of the funnel. Same thing happens in the galaxy, around the galactic center black hole. This is just for illustration. This is what happens at the center of our own galaxy. And I'll repeat again that the distance from us to the galactic center is 25,000 light years. And you can see the measuring scale here, which hold this picture is 10 light years. First of all, this little black star is a galactic center, black hole. Then the gray circle is a nuclear star cluster. It's the densest star cluster we know. The density of the stars there many times more than in any parts not only galaxy, in any parts of other star clusters we know. This yellow line is actually a galactic plane. It's a plane of our own galaxy because we are inside the galaxy, and so we see only the edge of it. And the galaxy rotates. This part where you see the dot, it comes toward you, and the other part goes away from you. So the galaxy rotates this way. Then there is big, and this nuclear star cluster rotates in similar direction as the rest of the galaxy. The red circle, which is actually the circle, just you see it sideways, is the circumnuclear disk that contains a lot of gas, cold gas on temperatures of about few Kelvin, which is minus 370, which is very cold, but for the galaxy, it's pretty normal temperatures. This spiral, which you saw in this movie I showed you, are actually three streams of the gas carrying the material toward the galactic center. Again, they're all the indication of their rotation, so they're coming away from this stream, goes into the board and coming on this side. And this one, the one which goes from east to west, rotates this way. And if we do a little zoom in on this circle there, you will see this blue orbit. This was one of the stars I showed you in the previous movie. That just gives you an idea of the scale and how much stuff is packed in it. Oh, sorry. And this one, the purple circle, was the orbit, was the star disk, which you also saw in the movie. All right, let's go to actually feeding the black hole. As we discussed, whatever is around the black hole is the most crowded region of the galaxy. You have lots of stars, lots of gas clouds, everything is in it. So what do you think is, whatever falls into the black hole, we consider it feeding the black hole. So the galaxy and surrounding feeds the black hole. What do you think the main thing which black hole eat? Would it be gas or would it be stars? Let's take a poll.
Yes.
Who think is going to be stars? Wonderful. Who thinks it's going to be gas? All right, perfect. Yes, of course, it's going to be gas. Because there is just way more gas in the galaxies than, in terms of mass, than stars. But the other thing important is just really hard to make star fall into black hole. You can think about this as, let's say, moon rotates around Earth. Earth has gravitational attraction. Moon wants to fall in. But because it has velocity, it always misses it. It always tries to fall, but it always just keep going around because it misses it. The same happens with the stars. For them to go into the black hole, you really need to slow them down. And it's obvious it's really, really hard to slow down the moon. It's much harder to slow down a star, which may be 15 solar masses. So we are not going to be concerned about the stars from this moment. Stars are going to be piercing the gas, the accretion flow itself. But we will be talking only about the gas. All right. Most popular picture in the internet of the black hole accretion, I think, is probably this one, where you have a black hole. The picture is, in many respects, is incorrect because your black hole is just a black thing in the center. But what we are looking at is the thin disk of the material orbiting the black hole. There are other images like this. And the only thing I want to point out here is this is not the one you've seen in the movie. It's the one with redshift properly attached to it, which was removed from the movie to avoid confusion. Yes. And actually, I think this is also an interesting thing to point out, that this is exactly the same system. This is a Saturn and a Saturn ring, and the Saturn ring are the accretion disk, and they are raining on the Saturn, and at some point they will be gone unless they're replenished. So this is exactly the same thing as black hole in the center and the disk, black hole in the center and the disk, and those are just the different images of the disk. This is a star and the disk which will later form planets, and this is actually an ALMA observation of this kind of disk. But what are the conditions for those disks to be thin? Because is it always this way? Are all the black holes, when they fit, you have a black hole, you have a thin disk around it, this stuff orbits, and then stuff goes in, and this is how your black hole get their food. Turns out, and it might sound counterintuitive, but for the disk to settle into the thin disk, you need to have lots of cooling. Cooling has to be efficient. But cooling only efficient when you have a lot of material. I'll try to explain it from the following perspective. Say you have gas. The gas falls toward the black hole. It gets, because of the friction, it heats up. It's getting hotter, hotter, and hotter. At some point, it gets so hot that protons and electrons are no longer together. They're ionized. They fly separately. So what happens is they fly separately in the same volume. They have huge velocities. If they pass by each other far enough, but not enough to recombine back to neutral atoms, they experience some kind of kick from each other. And this kick results from them emitting a photon. They cool down the same way as you would see me in infrared radiation. You will see these interactions in infrared and other radiation. So the gas gives away its kinetic energy, the energy of the velocity of those particles, and cools down. When it cools down, it settles on something more or less stable on the disk, because that's the only motion which is left, is motion on orbit around the black hole. And you can't really make it move. You cannot really make the disk very messy, because if you send the particle at a degree to the disk, it will collide at some point with the disk and would want to return to the motion of the rest of them, because it's just so inefficient for it to move at any other angle. But what would happen if you actually cannot cool your disk? Your disk pretty simply not going to settle into the thin disk, and you have, we still call it the accretion disk, but it's better represented by the phrase of accretion flow. It's a black hole in the middle and lots of gas everywhere, all around it. And I will play this movie. I will play this movie. Should go like this. All right, first of all, you see just a black hole appearing in the center. And you see the distortions of the stars right there. That's where a black hole is. There is no gas around it. It's just to show this is a black hole. At some point, the gas will appear, and then more gas, and then you see the structure of this accretion flow. Extremely hot gas moving around. Well, here it is, the gas is appearing. What's beautiful about this image is that if you use it on YouTube with your own cell phone, you can, it's 360 degrees, so you can move it around and look at different parts of the accretion flow. But it doesn't let me do it, right here. So you see lots of gas. You can't really say where there is no disk. There is some kind of general direction of rotation, gas getting thrown in different directions. It falls in. You'll get the jet motion appearing. It goes up. So why am I going through all this description? Is that naturally, when people started observing the center of our own galaxy, we all thought, the standard approach should be right. The disk at the center of the galaxy is supposed to be thin disk, because that's how a black hole works. But turns out, our own galactic center black hole does not work this way. It was that type of a black hole which has very little material around it. And because of that, particles cannot find each other to experience this interaction and to channel their velocity, their kinetic energy just into radiation. They cannot cool down. This is in a sense, it's a very, very big mess. Surprising part is that also the galactic center black hole is obviously the closest supermassive black hole to us. And all our models include rotation. We have never seen the rotation around our own galactic center black hole. To put it bluntly, we have theories of the type I was telling you that it doesn't cool, but I'm waving my hands, right? I'm not showing the equations. I'm not telling you it's going to be exactly this and this and this. So this is a very big and interesting problem, that accretion on our own galactic center black hole is a very mysterious thing. Yes. So part of, how much time do I have?
5 minutes.
5 minutes, perfect, thank you. Part of my own work is related exactly to studying the accretion in the galactic center. The reason we don't know everything about it is because it's, as I told you, it's a very bright region. It's covered with the dust. It's very hard to get through to it. So most information we have ever received from there in terms of how the gas around it works, how it moves, was coming from X-ray observations. And X-ray observations are sensitive to extremely high temperatures. When I say extremely high temperatures, I mean temperatures 10,000 times higher than the temperature in the sun. For that region, temperatures of the gas in the sun are actually cold, because 10,000 Kelvin for the galactic center is pretty cold, and this is the temperature in the sun. So because we observe in X-rays, X-rays do not have very high resolution. It's just a very difficult experiment. It's very hard to focus this kind of particles, this kind of photons. So we have a general understanding that the gas is distributed around the galactic center. But how? So one of my work was to study the other gas in the galactic center, the colder gas, the gas with a temperature of around the temperature of the sun, which is still extremely hot, but which wasn't studied globally from the point of view of accretion on the galactic center. And what we did, we actually discovered the presence of the disk of that type of gas around the black hole. The disk, in a similar way as I was telling you the rotation in the galaxy, you have a little disk around the black hole, and part of it, a redshifted part, this part moves away from you, and that part moves towards you. That's why one of the sides of this disk, its frequencies are shifted to the right side. The other frequencies shifted to the bluer side. And we saw rotation around the galactic center, which is pretty similar to the direction of rotation of the rest of the galaxy. So the rotation I just showed you in this picture is this blue line. And that part goes away from you, and this part comes toward you. And we were able to see for the first time actually rotation of the floor around the galactic center black hole. And with this, I think I'll just thank you very much for your attention, and please ask me all the questions.